Hi, my name is Matthew Tavares, and I'm a quantum researcher intern at HARP Research. The project I worked on was the HARP Graph 2 repo. This project consisted of visualizing a graph that can represent generalized graph structures with quantum-like properties. The graph structure is created through quaternions, I, j, k, and 1, which represent a superposition of all possible states, such as nodes, edges, and layers, as well as their corresponding interactions, such as pointing towards, away, and neutral. Here are the objectives. The first one was to create a gen graph directly without any quaternions. So this meant having functions like add node, add edge, add layer. And the next was to use quantum-like notation. This meant creating a node with quaternion I, an edge with quaternion j, then a layer with quaternion k. And then also an interaction. Here I use k and k, which means a neutral interaction for both of these. Next was to create and manipulate the gen graph with dictionary notation. So for edge 1, a positive interaction, vertex 1, a neutral interaction, and then layer 1, also a neutral interaction. And then finally, a fully working Hurwitz library where all operations can be performed on whole and half Hurwitz quaternions. Here is the output of a classical input. So this shows the edges, vertices, and layers, as well as spins. This is a more complicated one, but shows the features you can use. Here's the project progress. So the first deliverable was working on finding suitable notations and structures that can represent the gen graph on a quantum level. This leads into the second one, which is researching generalized graph theory, hypergraphs, and researching papers. Here we found a paper mentioning storing data as an atom. So these atoms can be nodes, edges, and layers all at one. So we found this to be most suitable. Next was updating the HARP Graph 2 repo to handle hypergraphs. This meant adding spins, layers, and direction. Next was adding a Hurwitz binomial class in Python to represent the different states on the gen graph. Then applying these Hurwitz quaternions to the HARP Graph 2 repo to then visualize how the whole quaternion sites can shape and affect the gen graph. And then finally researching methods to embed quaternions to quantum software to translate the graph quantumly, which is what I'm currently working on. Here's an output of the quaternion interactions, showing how an interaction can possibly go from a layer to an edge, and then also connect to another vertex. So it just shows the multitude of different interactions and things you can add by inputting Hurwitz quaternions. Here's a demonstration of the code. So here is the testing the graph class. So here are the classical features. You can add a hyper edge with vertexes here, layers with vertices here, spins, and here are just the classical features, but you can just directly implement things. Next is with two-site features, which adds inspiration from quantum-like properties. So you can add site 1 where I is a vertex, site 2 where j is an edge, and then interaction, positive for site 1 and then negative for site 2, which means going out from the vertex and into the edge. And this is what I'm going to demonstrate in a little bit. And then a couple other interactions using layers and vertices. And then also the multi-site feature. This means using a dictionary. So you can just directly, for edge 1, layer 1, etc., input the interaction you want for that specific interaction node. So here I'm going to run the code for this interaction here. So it leaves vertex 1 into the interaction node and then into the edge. So here's how I'm demonstrating the interaction between these two atoms. So my experience reflection. The skills I learned was in research, so literature review, reading papers, improving my Python skills, as well as learning new libraries like Matplot, GitHub knowledge and working on team projects, and then quantum computing knowledge, and especially learning how to apply this theoretical knowledge to the real world. Some roadblocks I overcame was having to learn new Python libraries like Matplot, as well as learning new advanced math topics like category theory, quaternions, some linear algebra concepts that I was not previously familiar with. My favorite part of the project so far was working on cutting edge technology that uses unique applications of quantum computing in theory, uh, as well as researching and discovering just new technology in general. I really enjoyed just the research aspect of everything, of learning and then applying it to these unique solutions. My least favorite part was probably coding the visualization tool with Matplot. I just felt like learning this new library of kind of visualizing and drawing the different shapes kind of took away from the quantum aspect for me a little bit, what I was mostly interested in. But now I'm working more with the quantum technology. So yeah, I'm excited for that. So in conclusion, thank you so much for this opportunity. I had a really great time. I learned so many new skills, so many unique topics, which I can only learn here. And I was inspired really to apply the applications of quantum technology to solve real world solutions. So thank you again.